Let's take a look at trig derivatives. This is one of my favorite topics out of this section. We are going to be looking at the derivatives of all 6 of our basic trig functions: sine, cosine, tangent, cotangent, secant, and cosecant. Now, before we can get into what their derivatives are, we first need to do some proofs. Because again, as always, if I just go through and tell you, hey, these are your derivatives, memorize them, well, it's empty knowledge if you don't know where it comes from. So let's first of all talk about where the sine function's derivative comes from. Whenever we're trying to prove the derivative of anything, we can always fall back on the limit definition of a derivative. We know that that's true for every single function in existence as far as how to prove their derivative. So I know f prime of x for any function f of x is equal to the limit as h approaches 0 of the function evaluated at x plus h minus the function evaluated at x divided by h. Now, in our problem, f of x is the sine of x that we're trying to prove the derivative of. So this limit definition of a derivative becomes limit as h approaches 0 of the sine of x plus h minus the sine of x all over h. Now my goal is to simplify this limit definition of a derivative so I can show what the derivative of the sine of x is. Okay, now, in order to do that, you're going to have to use the sine sum formula from your pre-calculus, I should say trig knowledge. I always say the sine of a plus b is sine a cosine b plus the cosine of a sine b. Well, if we have the sine of x plus h using that exact same summation formula, you could say, well, the sine of x plus h is the sine of x, the cosine of h, plus the cosine of x, sine of h. That is due to trigonometry formula that we've proven before in trig classes. Now, using that formula, I can expand out the sine of x plus h to this. That's what I've done in this step. So now I have the limit as h approaches 0 of sine x cosine h plus cosine x sine h minus the sine of x. In the next step, I say all I'm doing is I'm rearranging the terms up top. Well, what do I want to do? I want to gather the sine x terms together. So you'll see I have my first term sine x cosine h minus the sine of x, and then I put the second term last. Remember, order of addition is irrelevant, so it doesn't matter if I add the second term second or if I wait to add it third. Doesn't matter. Now, all of that's still divided by h. What I'm going to do in the next step is I'm going to distribute that h first into the first 2 terms and then into the third term. So I'll get the limit as h approaches 0 of sine x cosine h minus the sine x over h plus cosine x sine h over h. Now, again, you know that this is a legitimate algebraic maneuver because you could say, well, I could easily add these 2 fractions and it would just work backwards to this step. Okay, now, why did I separate it up like that? Because now you can factor out common factors in each of your numerators. In the first term, you can say, well, both of those terms have a factor of sine x. I can factor that sine x out in front. When I do, I'll be left with cosine h minus 1 over h inside of that. Remember, this sine x is no longer divided by h when you factor it out. It's understood to be over 1. If you took sine x over 1 times this expression, it would give you that fraction back. Now, in the second fraction, the only thing I'm going to factor out of that numerator is the cosine of x and leave the fraction as the sine of h over h. Why do we want this? Well, hopefully you remember from, I think it was section 2.6, when we were looking at trig limits, and 2 of those, it was in the squeeze theorem section, 2 of those formulas I said that will come up later were the limit as h approaches 0 of the cosine h minus 1 over h, and we said that was equal to 0, and we also showed it graphically. and the limit as h approaches 0 of the sine h over h is equal to 1. That was in fact, that was the very first graphical representation that we showed back in section 2.2 when we were looking at limits. The very first limit we looked at was the limit as x approaches 0, the sine x over x, and we showed that as you approach 0 from either side, the y value was going to 1. That's all I'm saying here. Since the limit as h approaches 0 of this first fraction is equal to 0, and the limit as h approaches 0 of the sine h over h is equal to 1, we know that this difference quotient limit is going to become, I have the limit as h approaches 0 of sine x times cosine h minus 1 over h plus cosine x over sine h over h. Well, what am I doing from this step to this step? I'm taking the limit as h approaches 0. Notice as h approaches 0, there is no h to plug into this term, so I just have the sine of x times 0 plus, again, there's no h in this term, it's just the cosine of x, but then the sine of h over h is 1. So you can say, well, then this derivative definition simplifies to just be 0 plus cosine times 1, which is cosine of x. Thus, we have proven that the derivative of the sine of x is the cosine of x using the limit definition of a derivative. Now, our other derivative formulas that we will need to know, and like I say, know them well. If you don't know every one of these 6 trig derivatives, I guarantee you'll miss a problem on our first test due to not knowing any one of them. They are absolutely mandatory memorization. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of I always remember secant and cosecant, they're the only two that have themselves in the derivative. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. One other thing that might help as far as memorizing your derivatives, I would advise you to keep in mind that anything starting with a co always has a negative derivative. That's not just true for these 3 functions, but throughout anything that we ever take the derivative of, if it starts with a co, then its derivative is going to be negative. So derivative of cosine's negative sine, derivative of cotangent, negative cosecant, derivative of cosecant, negative cosecant cotangent. Now, on my next page here, before I started the problems, the very first thing I said is, now I want us to be able to prove all the remaining trig derivatives. So I went ahead and did that and had fun doing it. Notice here, if I ask you to prove that the derivative of cosine is negative sine, the only 2 that are going to require the limit definition of a derivative are the sine and the cosine. They're going to be the long proofs. Then after I establish, using the limit definition of a derivative, that derivative of sine is cosine and derivative of cosine is negative sine, once I prove that, then those 2 ideas can become axiomatic. What does that mean? It means I can use those facts in any further proofs. So you'll see whenever I prove the derivative of tangent, I don't use the limit definition of a derivative. Neither do I for any one of the other 6 trig derivatives. I just put it into terms of sines and cosines and use what I've already proven their derivatives to be to find the derivative of the new trig function. So the only 2 that are really challenging are sine and cosine. Here, if I'm asking you to prove that the derivative with respect to x of cosine x is negative sine of x. So you say, well, when in doubt, the one thing that we can always do is use the limit definition of the derivative and say, well, I know that the derivative of the cosine of x is the limit as h approaches 0 of the cosine function evaluated at x plus h minus the cosine evaluated at x divided by the change in the x values, which they're h units apart. Limit definition of a derivative. Now, I need to expand out that cosine of x plus h. Again, hopefully you remember from trig, your cosine sum formula, it's always cosine, cosine, sine, sine, change the sign in between. Cosine of x plus h is cosine x, cosine h, minus the sine of x, the sine of h. So I can say, well, this is equal to the limit as h approaches 0 of this expression minus the cosine of x over h. Now, I want you to see the similarity of the sine proof with the cosine proof. Once I use the trig identity to expand the cosine of x plus h, what's my next step? I'm going to gather the terms of cosine x together. And this time I went ahead and separated them at the same time. So I said the first and last term can be put here, the cosine x, cosine h minus cosine x all over h. And this is, of course, still inside the limit as h approaches 0. But then this middle term, I separated out and said, well, minus sine x, sine h over h. Please notice, I have not changed a thing. I've just rewrote it into an equivalent fashion. If you subtracted these two fractions, you'd get back that fraction. So this is equal to this. Why is this superior? Well, because now I can look at that first fraction and say, well, why not just factor a cosine out of that fraction, and you would have cosine x times the expression cosine h minus 1 over h. In your second expression, you could say, well, I could pull a sine x out in front and get sine h over h. And then we've already proven these two. The limit as h approaches 0 of the cosine h minus 1 over h is equal to 0. The limit as h approaches 0 of the sine of h over h is 1. So all I'm doing from this step to this step is I'm taking that limit. That's why the limit as h approaches 0 has disappeared. I can say the derivative with respect to x of the cosine function is the cosine of x times 0 minus the sine of x times 1. Well, it's the negative of the sine of x then. Quod erat demonstratum, done with the proof. Gorgeous stuff. Now, you're thinking, well, okay, I don't want to do the other 4 trig derivatives. They're going to be hard. No, 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 no. They're really easy and really quick. Notice, when I take the derivative with respect to x of the tangent function, and my goal is to prove that it's equal to the secant squared, here's what I do. I can say, well, the derivative with respect to x of the tangent of x, it's the same thing as saying the derivative with respect to x. We know tangent is sine x over cosine x. What am I going to do now? I'm going to use the quotient rule. And I can say, then all I have to do is square the denominator, bring that denominator to the numerator, times the derivative of the numerator. We've already proven derivative of sine is cosine. Now, that's denominator times derivative of the numerator minus the numerator times the derivative of the denominator. And again, we've already proven derivative of cosine is negative sine. So I use what has already been proven as axiomatic in this proof. So now I can say, well, this is going to give me cosine squared. This is going to give me plus sine squared. I already know cosine squared plus sine squared is 1. So I can say my numerator cosine squared plus sine squared over my denominator cosine squared simplifies down to 1 over cosine squared. And then I know cosine is the reciprocal of secant. So 1 over cosine squared is the reciprocal of secant squared. And I can say, once I get to that, I have proven that the derivative of the tangent of x is secant squared x. Thus, I'm done with my proof. Quod erat demonstratum. Now, for the cotangent proof, I know that the derivative of the cotangent, it's the same thing as saying, well, what's the derivative with respect to x of cosine over sine? And then I can say, okay, the quotient rule, I square the denominator, bring that denominator up to the numerator, times the derivative of the numerator. Derivative of cosine, we've already proven, is negative sine. So this is your low d high minus high, your numerator cosine of x, d low, times the derivative of your denominator. Derivative of sine of x is cosine of x. Now look what you have. It's similar to the last one, except this is going to be a negative sine squared x, and this is going to be minus cosine squared x. So I have negative sine squared x minus cosine squared x all over your denominator squared, which is better written as sine squared x. And then you can say, okay, now in that numerator, I could factor out a factor of a negative 1 If I did that, it would give me a positive sine squared plus cosine squared. Well, now I know sine squared plus cosine squared, that's just a factor of 1. So my numerator is negative 1 times 1 over that denominator. It's negative 1 over sine squared. And again, I know that sine is the reciprocal of cosecant. So negative 1 over sine squared is going to be negative cosecant squared x. Quoterat demonstratum. Gorgeous. For the next one here, you're thinking, well, this can't get any more fun. They're all fun. If I ask you, hey, prove to me that the derivative with respect to x of the secant of x is secant x tangent x, it doesn't really make sense that the derivative would involve the original function as a product of terms inside the derivative answer. Well, let's prove that that is indeed the derivative. So I can say, okay, if I'm trying to show the derivative of the secant of x, I know secant's the same thing as the reciprocal of the cosine. So I can say, well, let's take the derivative of 1 over cosine x. Now, please remember with this ddx notation, that's an operator saying you need to take the derivative with respect to x. Once you start using the quotient rule to take the derivative, that ddx disappears. So the derivative with respect to x of 1 over cosine x is equal to, I square the denominator, bring the denominator up to the numerator, times the derivative of the numerator, but derivative of 1 is 0, minus the numerator, now times the derivative of the denominator. And we know derivative of cosine is negative sine. So now when I simplify, my first term's just going to be 0, and then I'll have plus the sine of x. My numerator is just sine of x. My denominator is cosine squared x. So now I look at what I have, and I look at what I need. I need the first term to show me that it's equal to secant. And I can say, well, secant's just 1 over cosine. Is 1 over cosine a factor of this quotient? Sure it is. I'll say this quotient is the same thing as 1 over cosine, and if I factor that out, my other denominator would have a remaining factor of cosine. My other numerator would have a sine, so I can say, well, this is equal to 1 over cosine times sine over cosine. 1 over cosine is secant, sine over cosine is tangent. This is secant x tangent x, quoterat demonstratum. For the last of our 6 trig derivatives, we're supposed to prove that the derivative of the cosecant function is negative cosecant x cotangent x. Okay, so derivative with respect to x of the cosecant of x. That's the same thing as saying what's the derivative with respect to x of 1 over the sine of x. So then I can say quotient rule on this. Square the denominator. Bring that denominator up to the numerator. Multiply that by the derivative of the numerator, but the derivative of any constant is 0. So low d high minus high, the numerator, minus 1, times the derivative of the denominator. And again, we've already proven derivative of sine is cosine. So now when I simplify this, my numerator is just going to be 0 minus the cosine of x, negative cosine x, over your denominator of sine squared x. And again, I look at what I have, I look at what I need, and say, okay, that first term is a negative cosecant. That's the same thing as negative 1 over sine. Could I factor a negative 1 over sine out of that? Sure, I will. Now, when I factor a negative 1 out of that numerator, it's going to leave me with a positive cosine for my other term, and I'll have another factor of sine in the denominator. Well, this is going to be your negative cosecant. This is going to be your cotangent. So I can say, yeah, this is clearly equal to negative cosecant cotangent, which is precisely what it was supposed to be equal to. Quoterat demonstratum. Now, those are the 6 trig derivatives. I want you to be comfortable with all of those, including the sine and the cosine that use the limit definition of the derivative. But remember, you never have to use that limit definition of a derivative after the sine and cosine, because once you've established what their derivatives are, then you can use those facts in for the other 4. Okay, now, if I look at my problems here, I ask you to differentiate f of x is equal to 5x cubed times the sine of x. So I can say, okay, no problem. I do need to understand that it is a product rule. I have a differentiable function times a differentiable function. So I would say, well, the derivative is going to be the derivative of the first, which is going to be 15x to the second, times the second, plus the first, 5x cubed, times the derivative of the second. Well, derivative of sine is cosine. Now, you could leave your answer like that. I would like you to go ahead and get used to be factoring your answers. So when I look at this, I can say, well, I could factor out a 5x squared. And if I did factor out a 5x squared, I would be left with 3 sine x plus x cosine x as my remaining factor. I would always prefer a fully factored final fantastic form of the answer. The second question I had here just had a quotient, and I asked you to find the derivative. So if this is g of x of secant x over 1 plus tangent x, then I can say, well, then the derivative of g with respect to x is equal to, quotient rule always tells us to square the denominator, and please keep in mind, I would never want you to physically square out that 1 plus tangent x. So please don't think you're getting a superior answer if you say, well, I'm going to call that denominator 1 plus 2 tangent x plus tangent squared x. Your answer is inferior if you do that, not superior. So it's better left in factored format like that. So now I'll say, okay, leave the denominator squared, then bring that denominator as a factor up to the numerator times the derivative of the numerator. So low d high. Well, derivative of secant, we just proved it right up here. Derivative of secant is secant tangent. So I can say low times the derivative of the high function is secant x tangent x minus high secant x times the derivative of the low function. Well, that's the derivative of 1 plus tangent x. We know that the derivative of 1 is 0, but then the derivative of tangent x is secant squared x, which is where this comes from. So now I can say, okay, my derivative has been taken correctly. However, I would not want you to leave it in this format. You should never leave terms multiplied if it's not a factor in that whole part of the fraction. So you say, well, this isn't multiplying everything else in the numerator, thus it's not a factor in the numerator, which means I need to distribute the secant tangent times both of those terms. And now we get secant x tangent x plus secant x tangent squared x. That's those two terms. And then my last term clearly is minus secant cubed x. Now I look at all three terms in the numerator and I can say, well, okay, I could factor a secant x out of all three of those terms. And when I do, I'll be left with tangent x plus tangent squared x minus secant squared x. And I would have my fully factored final fantastic form of the answer. Now, for number 3, I give you a function and I ask where that function has a horizontal tangent line. And you can say, well, anything horizontal, where it would have a horizontal tangent, horizontal lines have 0 slope. So if I ask where the tangent line would be horizontal to this curve, I'm just saying, take the derivative, set it equal to 0, because horizontal tangent lines are going to have a 0 slope. So it's asking you at what x values on the original curve is this slope going to be 0. Most of these values would be points where the curve hits a maximum or minimum point, because anytime it hits a maximum or minimum, it's going to have a 0 slope at those points. So I'll say, okay, here's my f of x in this case. If I take the derivative of x is 1. Derivative of cosine is negative sine. So the derivative of negative 2 cosine x is positive 2 sine x. So you could think of that as negative 2 times a negative sine, which makes that positive 2 sine x. Now, I take this derivative, set it equal to 0. Pretty easy to do. I subtract 1 on both sides, I get 2 sine x is negative 1. Then I divide by 2, and it's asking me, when is the sine of x equal to negative 1/2? These will be the values at which the tangent line is going to be horizontal. Okay, so I just need to be thinking of my unit circle, and we know in the unit circle, the origin is when x and y are 0. We know this is when y is negative 1 straight down, so negative 1/2 is about right here. the 2 points on the unit circle such that the y value is -1/2 is right here and right here. So I go down to a y value -1/2, find the two values on the unit circle. I know it's in quadrant 3 and it's in quadrant 4. In quadrant 3, it's pi/6 radians beyond half a revolution at 7 pi/6. And in quadrant 4, it's pi/6 radians before you get to 2 pi, which is 12 pi/6. So it's at 11 pi/6. And I went ahead and put what the coordinates for both the cosine and sine would be at each of these values. Of course, we only need the sine. So you can say, well, within one revolution of the unit circle, your angles are 7 pi/6 and 11 pi/6. I didn't limit my question to just asking the values of theta between, or in this case, I should say x between 0 and 2 pi. So I had to put the general answer. So you could say, well, you're going to have the sine value being -1/2 at 7 pi/6 or any coterminal angle to that. So in order to handle the coterminal angle over here, I just had to add the 2k pi. That's going to handle any revolution of 2 pi radians, whether it's revolving counterclockwise or clockwise. Either way, it's going to handle that because k is understood to be an integer. So you can say, well, 7 pi/6 plus 2k pi and 11 pi/6 plus 2k pi would be our two answers that will handle every single angle at which this function will have horizontal tangent lines. So, and of course, since cosine is a cyclical function, it's going to have infinitely many points at which the original has horizontal tangents. If you wanted a finite number, you would have to restrict. You'd say, well, just from like x equals 0 to 2 pi, and then of course you just have those two. Now, for the next problem here, I gave you a little application. I say a mass on a spring vibrates horizontally on a smooth level surface. So smooth level surface meaning that it's not going to have any friction whatsoever. It's just going to keep on going and going and going. The equation of motion of the mass, and you can see it's going to keep on going forever and ever because the horizontal position, that's why you're given position as x, it's only moving horizontally. The horizontal position, x with respect to time, is equal to 8 sine t. Now, so what that means is it's going, since the sine function has a range of -1 to 1, I know this could go out to a maximum of 8 times 1, which means it's going to go 8 centimeters beyond its natural position. And then on the other side, it's going to go 8 centimeters shorter than its natural position. So since x can go between -8 and 8, then I know that this can be stretched out to 8 centimeters beyond, and it will condense to 8 centimeters less than its natural position. So at x equals 0, that would just mean the natural length of the spring. But it's being stretched out, and then it's going back and forth and back and forth. Now, I'm asking you in part A here, find the velocity and acceleration at time t. Okay. So in order to do that, I just said I was given my position. It's a horizontal position function, 8 sine t. The velocity is just going to be the derivative of that position function. V of t is going to be 8 cosine t. Now, the acceleration would be the second derivative of position or the first derivative of velocity. And then the acceleration function is, derivative of cosine is negative sine, so derivative of 8 cosine is -8 sine t. So now I have all my position, velocity, and acceleration functions. The part B in this problem, I'm just asking you to evaluate these functions at 2 pi over 3 seconds. Okay, so at 2 pi over 3 seconds, the position function, if you plugged that in, it's going to be 8 times the sine of 2 pi over 3. You need to be thinking, well, 2 pi over 3, that's in quadrant 2, pi over 3 units above half of a revolution. At that value, your y value is the square root of 3 over 2 on the unit circle. So you can say 8 times the sine of 2 pi over 3 is 8 times the square root of 3 over 2. That's going to give me 4 on the root of 3 centimeters. So what I know is that the spring, as I have pictured, it's pretty far beyond its natural length right now. So its natural length would be at this position of 0 centimeters. It is stretched beyond that. But here's what we don't know. Just by knowing the position, we don't know if the spring is still on its way extending outwards or if it's already on its way back inward. How do we know? Well, we're going to take the we're going to take the first derivative and we'll evaluate it. What if the velocity is positive? If the velocity is positive, it's still going out. Well, what if the velocity is negative? Clearly, it's contracting back inward. So right now, just by evaluating the position, I don't know if the spring is still extending outward or if it's going inward, but I can quickly find out. When I go to my velocity function and evaluate it at 2 pi over 3, I get 8 times the cosine of 2 pi over 3. Well, the cosine at 2 pi over 3 is -1/2. This tells me that my spring is going inward at a rate of 4 centimeters per second. So I know at the point in time I'm interested in, at 2 pi over 3 of a second, the spring is extended beyond its natural length, but it is going inward. It's going towards the wall. So I can say, okay, it's going to the left, towards the wall. Well, what's the acceleration? The acceleration here function, that was our second derivative of position, first derivative of velocity. I had the -8 sine t, so obviously it's just the negative of what the position function, -8 times the square root of 3 over 2. I get -4 on the root of 3. Now, keep in mind the units, it's change in velocity over change in time, so that's -4 on the root of 3 centimeters per second each second, or centimeters per square second. So now, when I'm thinking about, well, what does this mean? It means that the spring is going in towards the wall, and the rate at which it's going in towards the wall is speeding up. Now, how do I know that the mass is speeding up? Well, we're supposed to know. And if you think about that, so often students mistake the sign on the second derivative. They say, well, wait a minute, that's wrong. You can't say it's speeding up because it has a negative acceleration. I most certainly can say it's speeding up because it has a negative acceleration, because whether a particle speeds up or slows down is just an effect of the sign of the velocity and acceleration. The fact in this case that the velocity and acceleration both have a negative sign means it's moving in towards the wall, and the rate at which it's moving in towards the wall is increasing. So it is speeding up because the sign of the velocity and acceleration functions are the same. The only time that a mass is going to slow down, and I put here, you would slow down if the velocity and acceleration have opposite signs. So what we typically think of, and we say, oh, well, it's decelerating. Well, that's because we normally think of the velocity as positive. If you're driving in a car and you're going forward, and you apply your brakes, then you're decelerating because that velocity is slowing down. You have a negative acceleration. So the only time you slow down is when the signs of the velocity and acceleration functions are opposite of one another. Anytime they're the same, in this case they're both negative, the mass is going to speed up. In this case, it's just speeding up in a negative direction. Now, the last cool problem I'll look at here, I ask you, what's the 51st derivative of the sine function? Now, does that mean we're going to take the derivative 51 times? No. It'd be kind of cool sometimes, but actually in this one it'd be rather boring, because you would see after the fourth derivative it just starts repeating itself, as all cyclical functions derivatives will do. Okay, so if the original function is the sine function, we have shown that the derivative of sine is cosine. We also know that the derivative of cosine is negative sine. So I can say, well, my second derivative is negative sine. Now, I already know that the derivative of sine is cosine, so the derivative of negative sine would be negative cosine. So I get the third derivative is negative cosine, but then you can say, yeah, but the derivative of cosine is negative sine, so what's the derivative of negative cosine? Positive sine. And then you can see, so the fourth derivative goes back to the original function. And that's what I want you to see. Well, if I said, well, take the fifth derivative, it'd be the same thing as the first derivative. Sixth derivative, same thing as the second. Seventh derivative, same thing as this. So this function y equals the sine, and cosine would be the same. It's going to complete its cycle of derivatives every fourth derivative. So each fourth derivative is going to go back and just become the original function. So what I did to show how we would take the 51st derivative, you just need to find what's the remainder of that 51st derivative with the fourth derivative, because we know every fourth derivative, it goes back to the original function. So I just said, well, 4 goes into 51, 4 goes into 5, 1 time, bring down, or sorry, 4 times 1 is 4, 5 minus 4 is 1. And then you can say, well, 4 goes into 11 2 times, and 2 times 4 is 8, 11 minus 8 leaves a remainder of 3. So that's long division algorithm. We don't normally do that too often, but you could just say, well, all right, John, you just said 4 goes into 51 12 times with a remainder of 3. I know 12 times 4 is 48. 48 is 3 numbers away from 51. That tells me that the 51st derivative, it's the exact same thing as the third derivative. And then I can say, well, what is my third derivative? It's the negative cosine of x. Thus, that's our answer for the 51st derivative. All right, guys, this does it for the notes for section 3.6. Please do try the Achieve homework assignment for this section. Just got through doing it myself, and there are some fun problems in it. Please let me know if you have any questions. I'll be glad to help at any time.